Okay, welcome to electrical machine lecture. Our today topic is Hopkinson test. It is also called as a back-to-back or regenerative test. Back-to-back and regenerative test, it means that here two machines are used. One machine acting as a motor and second machine acting as a generator. Therefore, uh, whatever the motor output is connected to the generator mechanically, and the generator output is connected again back to the motor. So therefore this test is called as a back to back test, and the power drawn from the supply is very small because it takes only the no load power for both the machine, or it will the power input to the motor generator set is used to overcome the stray losses. Now, in the previous two section, one is the direct load test, second is the Swinburne test. We found that there are advantages in the direct load test is that whatever the efficiency is at actual load condition, where it is possible to observe mechanical vibration, sound, temperature rise, and commutations. But this method is applicable for small capacity because it requires large amount of power at the same times mechanical loading arrangement. So this method is not applicable for higher capacity in the labs. Whereas the Swinburne test is the no load test. Here, no load data is sufficient to calculate the efficiency at desired load condition. So higher capacity machine can be tested, but this is the no load test. So it is not possible to observe the temperature rise, mechanical vibrations, sound, commutations, and this one. So these two advantages are clubbed into the Hopkinson test, where two identical machines are taken, and by this two identical machine, it is possible to load to its full load value. One acting as a motor, second acting as a generator. So generator is such a the generator excitation is adjust such that it will supply the more current and it is equal to the full load current of the motor and so on. So this is the circuit diagram. The power supply is taken at a rated voltage V. This is the current IL. So power input to the generator motor set is V into IL. Whereas the motor output is connected to the generator and generator output is connected to the motor. So the power drawn from the supply will be smaller. This is the major advantage of back-to-back test or Hopkinson test. Now procedure first, select the instrument as per the rating of the machine. Select the voltmeter whose values not more than 0 to 300 because it is going to observe the voltage across switch. Now run the motor at rated voltage and rated speed. It will run the generator and it will generate some voltage. Now adjust the generator excitation in such a way that the generated EMF is equal to the supply voltage. It means that the voltage across switch is near to zero. Now adjust the field current till the voltage across voltmeter goes to the zero value. As soon as it goes to the zero value, switch is closed or close the switch. Now generator current is going to supply to the motor. Now suppose if you increase the excitation current, it will generate more voltage. So this more voltage is going to supply current to the motor. So definitely in this set, it is quite obvious that generator will supply the current only when the generated voltage is small greater than the terminal voltage of armature. So this is the procedure as discussed. So it is written in the same way. Select the range of the measuring instrument as per the rating of the machine. Select the voltmeter 0 to 30 volt across the switch. Run the first machine as a motor at rated speed at rated voltage by adjusting the rheostat which is connected in the motor field circuit RM. Adjust the rheostat RG, that is the generator voltage, till voltage generated by the second machine close to the rated voltage, adjust the rheostat RG. This is the rheostat which is connected in the field circuit of generator. Observe the reading of voltmeter connected across switch S till it reads zero voltage. Once the voltage deflection is zero, close the switch. So it is very much necessary that before conducting the practical, we should ensure that the switch is open. Increase the second machine field current till it generates voltage greater than the applied voltage and act as a generator. Adjust the field current. This field current ISHG, that is the shunt field current of the generator, uh, it will supply more current to the motor, armature current to the motor. Now adjust the field current ISHD of the generator till armature current reaches to rated value. Now both machine under the full load condition. So this is the procedure one by one. You load the motor, you increase the excitation of the generator. It will increase more current in the, it will inject more current in the motor side and so on. So this is the supply voltage. This is the current drawn from the supply. It is the generator current, sorry, it is the motor armature current. It is motor field current, speed of generator motor set, generator armature current IAG, and generator field current. Now we will do the calculation. So for that calculation, say, uh, first we will see the power input. Say here we have considered the same diagram for our consideration. Here the power input to set is equal to V into IL. V is the supply voltage and IL is the current which is for both the machines at no load condition. At no load condition. This is the no load condition. Even in the load condition also, this power input will remain same. Okay. Now, uh, generator armature CU loss is equal to generator current IAG is square R. Let the generator resistance is RAG, armature resistance RAG. Similarly, motor armature CU loss, which is equal to IAM, is the motor armature current square into RAM is the motor armature, is used to overcome the stray losses in the both machine. Okay, stray losses in the both machine. Here the switch is closed. The switch is closed in this condition. Okay, so so whatever the power input is used to overcome the stray losses, if you subtract these two variable loss in the armature of the generator as well as motor, we get uh, total stray losses, total stray loss, that is iron frictional and windage loss, that is iron frictional and windage loss in both the machine. Okay, so therefore total stray losses, total stray loss is equal to power input power input minus no load, or we can write here it is the minus armature cu loss in both the machines. No doubt it is power input to set at no load condition. It is the no load condition. So the armature cu loss, all these things are the no load cu loss, no load condition. So power input V into IL minus armature copper loss in the generator. It is IAG square RA plus motor RAM. So this is the generator and this is the motor copper loss at no load condition. This is at no load condition, at no load. Okay. So instead of writing more and more nomenclature, uh, we will simply write at no load condition. Now, the efficiency, we will say this is equal to, we will give the name as a W stray loss. This is the total, or only we will say this is the W only. The losses, stray loss is W. Now, stray loss per machine, since the machines are identical in type as well as the capacity, it is equal to W divided by 2. This is for the input power for the both the machine set. So it say it is WS for each machine is the stray loss. So say we will call as a stray loss. Now, first we will consider as a efficiency of motor. Efficiency of motor. We are going to calculate the efficiency of motor. So motor input is equal to armature input plus armature input plus shunt field input. So this is the at load. At load. These are the calculation at load condition. So it is equal to armature input is nothing but V into IAM is the armature input plus shunt field current ISHM into RM is the shunt field resistance as it is given. We can write ISH also. Plus say it is equal to motor input W M input. Okay, we'll give the nomenclature as W I M. It is the motor input. Now, what is the motor output? Motor output is nothing but motor input minus losses. So say motor losses is equal to armature cu loss. No doubt it's all load condition plus field cu loss plus stray loss. stray loss. So which is equal to IAM square RAM plus V into ISHM plus WS is the stray loss. So this is the total stray loss in the machine. Say we will give the name as loss. So WLM, motor loss. Okay. Now motor output is equal to motor input WIM minus WLM is the motor output, and therefore efficiency of motor is equal to output of motor WIM minus WLM divided by WIM into 100. So in this way, the motor efficiency can be calculated. And for the efficiency of generator, only what is that? In case of generator, the generator output is nothing but voltage which is appearing across the armature multiplied by the current supplied by the generator is Ig is the generator output, and losses is same, shunt field copper loss and armature copper loss plus stray loss. So here the generator output is, say we will write the equation only directly. So it is the generator efficiency of generator C of generator. So output of generator is V into Ig is the output of generator divided by output plus losses. Similar losses is going to calculate the same way. So it is V into Ig is the output of generator plus losses. Output plus losses is the total input. So WLG is the output efficiency of generator. So this is the way. It is look like somewhat difficult, but in the numerical, we are not using same nomenclature. We are writing the equation with the help of circuit diagram as per the question. So it become very simple and very interesting also. Now, what are the advantage? This method is economical because the power drawn from supply is small. Second, the temperature rise and the commutation condition can be checked under the rated load condition. Here, the power, both the machines are at load condition. Therefore, it is possible to observe the mechanical vibrations, sound, bearing condition, commutations, and temperature rise. Uh, Stray losses are calculated for the both the machines under operating the load condition also, and large machine can be tested since without consuming the much more power. So the auxiliary power requirement is less. Therefore, it is possible to conduct the test on the higher capacity machine. And efficiency can be determined at any load condition. It has one advantage, a disadvantage. The disadvantage is that for this method, we need two identical machines. So this is the advantage of Hopkinson test. So thank you for listening. Next time we will do some numerical based on the Hopkinson test.